Assalamu alaikum everyone. Today we have to continue this chapter number 8 and we will try to solve some of the examples and try to implement some of the equations that we have used in this chapter number 8. Okay. So let us start with this example 8.4. So using figure 8.4, so this one is a figure 8.4. Calculate the relative cost of providing refrigeration at 5 degrees C, minus 20 degrees C and minus 50 degrees C. From the figure, the ordinate values are given as follows. Okay. So what we are going to do here, we have to calculate the relative cost that is required for the refrigeration. Okay, so I will just take you back one figure. So we discussed this kind of the refrigeration cycle in the previous lecture, and we see that what could be the impact of this evaporator on the energy requirement for the whole process and mainly the compressor. And what we have seen that if we are getting more amount of heat at the outlet of the evaporator, then the compressor has to do more work and the coefficient of performance would be reduced. Okay, so for this kind of refrigeration cycle we can have this kind of graph that give you an information that what could be the temperature for this evaporator and how it would affect the coefficient of performance. Okay, so once you have the refrigeration temperature, okay, so you can follow this line and you can find out the value for the reversible work in the form of 1 divided by coefficient of performance reversible per unit of the cooling duty. So what we see here, if the coefficient of performance it is decreasing, then the value for this reversible work would be increased. Okay, so if you want to have more temperature reduction into the refrigeration cycle, then we have to spend more amount of energy. Okay, so what we can see here, okay, at 5 degrees C, you can see from here you can go to this line and then you can see what is the relevant value for 1 divided by coefficient of performance. Okay, so what we can actually see from here, that even if you go to minus 20, you can get the value for this parameter, and again at minus 50 degrees C you can have the value for this parameter. Now what we can actually see here, that the factor, this factor, it is going to increase. How it is going to increase? When we are having the less value for the coefficient of performance, then the value for this overall term it would be increasing. So what we can see here, if we want to cool something at a lower temperature, maybe minus 50 degrees C, then this factor value would be high. So how the value could be high? If the coefficient of performance is low. Okay, so from here we have to analyze that what could be the impact on the cost if we want to have some cooling at different temperatures. So what we can see from here, therefore, compared with the cooling at 5 degrees C, cooling to minus 20 degrees C is 0.257 divided by 0.144 times. Okay, so here minus 20 degree you can have for example this much energy requirement, or the this one is the reversible work per unit of the cooling duty. Okay, so you can see that if the value for this term it is going to high, then you have to spend more amount of energy and the cost for achieving this much cooling. Okay, so you can simply take the ratio of the of this vector with at different temperatures. Okay, so what we see here, if you are cooling something from 5 to minus 20, then you have to spend this much ratio more amount of money and energy to get this cooling. Okay, so this one times more expensive and cooling to minus 50. So if you go to minus 50 degrees C cooling, then you can take the ratio between 0.426 and 0.144 to get the idea about the cost. Okay, so it would be 0.426 divided by 0.44 times more expensive compared to the 5 degrees C. So this analysis assumes that two refrigeration systems operate equally efficiently with respect to the reversible limit, and that the major cost is the power to run the compressor. Okay, so what we see from here, if we can get like a very low temperature in the evaporator, or you want to refrigerate something at a very low temperature, then what would happen? The coefficient of performance it would be reduced, right? And if the coefficient of performance is reduced, then you would be getting more higher value of this factor, and if you're getting more higher value of this factor, then you have to spend more amount of energy and the cost to get the required temperature. Now let us see the second example. Example 8.5, obtain a cost estimate for the refrigerated cooling utility operating at 5 degrees C. Okay, so for this one is a process and the temperature that is specified here, it is 5 degrees C. Okay, so for this string number maybe 3, the temperature it is 5 degrees C and we have to estimate the cost for the refrigerated cooling utility. So we have to see that how much is the cost required for the cooling. Okay, so for this one, okay, let's see what we have. Consider a single stage refrigeration system to provide the refrigeration at 5 degrees C using this one is the name of the solvent that is used as a refrigerant. The process flow diagram and the operating conditions are given here. Okay, so this one is the diagram. Okay, so you can see this one is a diagram same. Okay, now at the string 1, 2, 3 and 4 you are provided with this information about the temperature, pressure and the vapor fraction. Okay, so stream number 3 which is given here, the temperature it is 5 degree. Okay, so here the temperature is 5 degrees C, that is given here. Okay, and we have to see that how much is the cost required for the refrigerating cooling utility. Okay, so what we can do from here, we have to calculate different things. Okay, first of all you can see that there is a compressor in the system, so you have to calculate what is the compressor power. Then there is a condenser and also there is an evaporator. So first of all we have to get the information on these three kinds of items that we have in the process flow diagram. So this information is provided to you. Compressor power it is given here in the data, that is 66.5 kilowatt, and the efficiency for this compressor it is 75%. Condenser duty it will be 1.25 gigajoules per hour, and for the evaporator duty it is 1.00 gigajoules per hour. Now we have to estimate what is the compressor work per unit of the cooling. Okay, so we are provided with the compressor power here. Okay, so you can have the compressor power here, and then you can like have the information on the evaporator duty, that is 1 gigajoule. Okay, so you can divide this one with the 1 gigajoule per hour, so you can convert that one into the second. So here you can have the compressor work per unit of the cooling requirement, that comes out to be 0.2394. This value compares with 0.144 for the Carnot cycle. The main differences are due to the inefficiencies in the compressor and use of throttling valve instead of a turbine. Okay, so what we see here for the Carnot cycle, you can have the value this one 0.144. Okay, and for this compressor you can have the higher value for this cooling requirement. Okay, so that is because that if you use some kind of turbine here, then you would maybe get less value for the compressor work. Okay, so the main differences are due to inefficiencies in the compressor and the use of throttling valve instead of the turbine. Now we have to calculate what is the cost of refrigeration at 5 degrees C. So we can see this one, the power for this compressor it is 66.5. So 66.5 is here. Then you can have 0.06 which is the electricity cost. So you can go back to the table 8.3, and there you can find out the value for the cost of electricity. So you can go to this table 8.3 here, and here you can find out the cost of this electricity here. Then 1.24 which is basically the condenser duty, and for this condenser duty you have to multiply this one with the cooling water requirement. Okay, so the cooling water you have to search from here table 0.354. so here the cooling tower water, okay, that comes out to be 0.354. So you have to multiply this one here. So the total value for the cost for refrigeration it comes out to be 3.99 plus 0.44. In terms of dollars per hour it is $4.43 per hour, and in terms of energy you can have $4.43 per gigajoule. Now using the results of the example 8.4 we can predict the cost of refrigeration at -20 and -50 degrees C. Okay, so you have the cost for this one at 5 degrees C. Now we can imagine or we can calculate what would be the cost at -20 degrees C. So we have to use the factor that we calculated earlier. Okay, for -20 degrees C, what we have here, the factor that we calculated it is 0.257 divided by 0.144. That comes out to be equal to 1.78. Okay, So we can multiply the factor 1.78 with this term to get the value for the cost of refrigeration requirement at minus 20 degrees C. And similarly, you can estimate the cost for the refrigeration at minus 50 degrees C. So you have to multiply this $4.43 per gigajoule with the factor that we calculated in terms of minus 50 degrees C. So here you have calculated the ratio for the cost requirement in case of minus 50 degrees C and its comparison with the 5 degrees C. So from here you can get the value around to 2.96 sorry 2.96. So you can multiply that number here with the term 4.43 to get the value for the cost of refrigeration. So what you see here overall that at 5 degrees C you have to spend less amount of money, but as the cost or as the energy or the temperature requirements are going low and low, then you have to spend more amount of cost for achieving that temperature. Okay. Now let us solve the example 8.3, and in this example we have to see some of the heuristics also that are maybe not provided directly into the tables, but you can see some of the heuristics as we solve this example. Okay. So estimate the utility cost for producing a circulating cooling tower, cooling water stream using a mechanical draft cooling tower. Consider a basis of 1 gigajoules per hour of energy removal from the process units. Flow of cooling water required to remove this energy equal to mass flow rate in terms of kg per hour. Okay. Now we have to calculate the cost of the utility for producing a circulating cooling water stream. Okay. So what we can do here, first of all, we have to estimate what is the total available energy into the system. So we can use a simple equation mcp delta t. So the mass flow rate we have to calculate. Cp for the water rate is 4.18. So you can see the relevant units. And delta T is the temperature. So for the cooling tower, we can see this range that it is between 40 to 30 degrees. So it goes into the cooling tower at 40 degree and returns at 30 degree centigrade. So you can put the values here. So that comes out to be 41,800 multiplied by the mass flow rate, and how much energy it has to remove 1 gigajoules per hour. So you can convert this one into the joules per hour. Now here you can divide the energy with the mass flow rate to get the value for this m dot. Okay, so you can divide this number with 41,800 and the mass flow rate into the cooling tower. It comes out to be 23,923 kg per hour. Now we have to see that what are the water losses from the cooling tower. So first of all, we have to, I will take you to the figure for the cooling tower. So here is a figure for the cooling tower. You can see this one here. So there is some addition of the water, that is the makeup water, and there is some blow down of the water which is going into the waste stream, and then there are some losses of the water in terms of evaporative and the wind losses. Okay, and cooling water, you can see the temperature range here again, and also you have seen some tables earlier in which this range is given 40 to 30 degree. Okay, so what we can do here, we have to calculate what is the evaporative water losses at 35 degrees C. So the value for the Cp that you have to calculate, or you can see the literature, that comes out to be 2417 kilojoules per kg. And now we have to calculate that how much is the amount of water lost due to the evaporative cooling, or due to the evaporation from the cooling tower. So the heat load for this basis 1 gigajoules per hour. You can divide this one with the Cp value to get the value for the mass flow rate. That comes out to be 413.7 kg per hour. Okay, so these are the losses from the cooling tower in terms of the evaporative losses. Okay, so how much is the percentage of this water compared to the total amount of water? So you can simply take the percentage here, 413.7 divided by 23,923, to get the value for the water losses from the evaporative or from the evaporation, okay, from the cooling tower. So that is 1.73%. Now we have to also calculate what should be the wind losses. So typical windage losses from the mechanical draft towers are between 0.1 to 0.3%. Okay, so you can see this value here, and maybe this is the literature value, and maybe you will not find this one directly into the heuristics, but you can use this example and you can have an idea that it should be between 0.1 to 0.3%. Okay, so we will use the value 0.3% in terms of the windage losses. So let's see what should be the value. Okay, so basically it is the direct percentage, so you maybe multiply this one with the mass flow rate to have an idea at how much should be the losses. Okay, now we have to calculate mainly to calculate the blow down. Okay, so this is another part, purge or the blow down. So what should be the losses of the water in the blow down? To calculate the blow down, we must know the maximum allowable salt inorganics concentration factor of the circulating water compared with the makeup water where the S is defined. Okay, so this blow down, it basically depends on the salt concentration within the water. So how you can find out that concentration? This is an equation here. S is a factor that represents you the concentration factor of the salts. So concentration salts in the cooling water loop. So this one is a cooling water loop, all of it. Okay, S of loop, and then concentration salts in the makeup water, and this one is the makeup water. So how much is the salts coming from the makeup water, and how much is the salt that is already available in this loop? Okay, so we have to find out this ratio. Typical values are between 3 to 7. So this ratio is usually between 3 to 7. Here a value 5 is assumed, so we will use the average value of 5 for this S factor. Okay, by performing a water and the salt balance on the loop as shown in the figure 8.3, the following results are obtained. Okay, so if you simply apply the mass balance of the water here, what you can do here, so the WMU, that is the makeup water, it would be equal to the water losses into the tower due to evaporation. Okay, W tower plus water losses due to the wind plus water losses into the blow down. Okay, so these are three losses. And in terms of the salt calculation, you can multiply this equation with the salts. Okay, how much are the water salts present into the system? So salt in, it is the number of salts or the amount of salt that is coming with the makeup water, and on the right hand side we can have the factors salts that are present into the loop. Okay, so you can have S loop here now with the wind plus S loop into the blow down. Okay, okay, obviously we will not include the value for this what we call in the evaporation, because the salts are not being evaporated, right? So it has to be within the system. So because S loop, that is equal to 5 times of S in. Okay, so we can use this value 5 here. So and the salts in the loops, it will be equal to 5 times of the salt into the makeup water. It follows that. Okay, so you can have this one salt in, and so for this makeup water you can use this equation again, so you can put it here, and for the right hand side it would be coming as such. Okay, so you can rearrange this equation in the form of waste blow down or the water in the blow down, and you can rearrange the equation. You can further simplify the equation in this form. So the final equation that you would get here, water going out of the system from the tower in terms of the evaporation divided by 4 minus water losses into the wind. Okay, so we have calculated this value for the wastage or the losses of water from the evaporation. It is 1.73%, and the water losses into the from the system from the wind here, it is 0.3%. So the overall uh, water into the blow down, it comes out to be 0.133%. Okay, so now you can estimate what should be the total value for the makeup water, which is equal to the this one 1.73, which is we just calculated here. Okay, 1.73%, and then we have the losses in due to the wind, and then we can have the losses into the blow down. Okay, so you can calculate the total percentage, and then you can multiply this percentage with the total water flow rate, that is 23,923. Okay, so you can have the value for the total makeup water, and that will obviously reflect that how much is the water is being going out of this system in terms of losses. Now the next part here, we have to calculate the power requirements and how much of the energy it is being utilized by this fan and how much is the energy utilized by this pump here. Okay, so we have to estimate what is the piping section here and how much is the pressure loss into this piping section, and then how much energy is required to overcome that pressure. Okay, so what we can see here, pressure drop around cooling water loop is estimated as follows. So delta P in the loop, it is 15 psi, and 5 psi in the exchanger losses, 10 psi in the control valve, 8.7 psi in the static head, and uh, because water must be pumped to the top of the cooling water estimated to be 20 feet above pump water, that is 838.7. So you can add up all of these pressure losses, that comes out to be 266.7 kilopascal. Okay, so obviously this information about these losses, it is not directly provided to you in the question, but from the exam point of view, some of the information would be given to you to estimate the total value for the delta P. Okay, so for this whole system, the delta P, it is 26 to 266.7 kilopascal, and then we have to use the equation for the pump to estimate the value for the energy. Okay, so we have used a similar equation, 1 divided by epsilon multiplied by volumetric flow rate and delta P. Maybe the earlier equation that we see in the heuristics, that was 1.67 and divided by epsilon multiplied by volumetric flow rate and delta P, right? So you have to be careful about the units here, and because the final unit, it should be kilowatt or watt. Okay, so you can use any of the equation depending on your ease. Okay, so the pump efficiency, it is given here, it is 75%. Okay, so simply what you can do here, 1 divided by 75%, which is an efficiency. You are provided with the mass flow rate. Okay, so you can convert that one into the volumetric flow rate, and you can make the relevant unit conversion. And delta P, we have calculated here 266 kilopascal. So the pumping power required, it comes out to be 2.36 kilowatt. Now the second part here, we have to also estimate the power required by the fan. Okay, now what are the different things that we have to consider here? From preference, the required surface area in tower is 0.5 feet square per unit gallons per minute. That the designed wet bulb air temperature is 26.7. From the same reference, the fan horsepower per square foot of the tower area is 0.041 horsepower per foot square. Okay, so some of the information is provided to you here, and you have to estimate the total power for the fan. So how you can actually do this one here? You are provided with the mass flow rate. Okay, so you can convert this mass flow rate kg per hour into kg per second. Okay, and then this is the relevant conversion of converting the kgs into the gallons. Okay, so you can make the relevant conversion for kg to convert the kg into the gallon. Then 0.5, it represent you the required surface area in the towers. Okay, and then you can have the information on the what should be the horsepower required per feet square. Okay, so when you multiply all of these terms, it will give you the information about the power required by the fan. Okay, so and the total value, it comes out to be 1.61 kilowatt. Now we have to add up all of these two powers, and we will see that how much is the electricity requirement. Okay, okay, before going to that electricity calculation, let's see what we have here. From a survey of the vendor, the cost of chemicals is 0.156 dollars per 1000 kg of the makeup water. So whatever makeup water you are putting here, the chemicals that are coming into this makeup water to avoid the foiling, to avoid the falling, or like some other like chemicals to avoid the fungus and bacterial growth. Okay, so usually there is some chemical addition, that is $0.156 per 1000 kg of the makeup water. Okay, now you have to use the electricity cost 0.06 kilowatt dollars per kilowatt hour from the table 8.3, and the process water cost also, that is $0.067 per 1000 kg. The overall cost of the cooling water is given by. Okay, so the equation that you can get here, cost of cooling water, it is equal to cost of electricity required in the pump and the fan, cost of the chemicals for makeup water, and the cost for the makeup water itself. Okay, so you can go to the table 8.3 and to from where you can see the relevant cost estimation. Okay, so 0.06, it is the cost for electricity. Okay, so here you can see that 0.06 dollars per kilowatt hour, it is the cost of electricity, and then here you are provided with the total energy for the pump and the fan. On the right hand side, 517, this number actually represent you the total amount of water that is going as a makeup water. Okay, so here this term you can multiply this one with the cost of chemicals. Okay, 0.156, that is coming from the literature to have the value for the cooling water requirement and the chemicals requirement. And then you can have the value for what is the cost of the water that you are actually adding to the system. Okay, so for this one, cost for the cooling water you can see from the table. Okay, so from here, from the process use water, okay, so the value is also given here, $0.067 per 1000 kg. So you can put this value here in this equation, and then you can simplify this equation to get the total cooling water cost that comes out to be $0.354 per hour, or $0.354 per gigajoule. Okay, so this is about the example 8.3, and next time inshallah we will try to solve few examples relevant to the chapter number 8. And this is all for today. Let me know if you don't understand anything. Okay, thank you.